In this lesson, we're going to be talking about just real basics of matrices. We've seen them before, certainly when we did cross product and so on. We're going to talk about them a little bit more, um, and then we're going to get really into something called eigenvalues and other things associated with that. So I want to just really briefly say again, we're just getting the real basics of matrices. For those of you who go on to take linear algebra in a later course, that's going to get a whole lot more detail as far as matrices. This is just a real beginning of that conversation. So first off, matrix, we've already seen these, as I said. It's an array of numbers. And so, for example, if I wanted to do 2 times a matrix, so 2 times A, that's the same as just multiplying each entry by a 2. So 2 times 2 is 4, 2 times -1, 2 times 3, 2 times 0, 2 times 4, 2 times 6, 2 times -6, 2 times 10, and 2 times -5. Again, multiplying by a constant, really not a big deal. And by the way, I guess I should back up here real quick and say I'm really not going to tell you a whole lot of stuff with matrices, and in fact, I'm even talking in this video. I'm going to do less than I even usually do with this class. I'm just getting the parts of the matrices that are going to be necessary for us to understand the conversation about eigenvalues, because that's really going to be the part that's going to be important that we're going to be using in for the rest of this course. So anyway, this is what it means to multiply a constant times a matrix. If I wanted to add two matrices, it really is just a matter of adding the corresponding parts. So if I do A plus B, 2 plus 4 is 6, -1 plus 7 is also 6, 3 plus -8 is -5, 0 plus 9 is 9, 4 plus 3 is 7, 6 plus 5 is 11, -6 plus 1 is -5, 10 plus 1, -1 is 9, and -5 plus 2 is -3. Okay, so again, adding two matrices, no big deal. It's just just add the corresponding pieces. Um, we're really not going to get into, we're really not going to get into what it means to multiply two matrices. That's a bit of a conversation. But the one part about multiply matrices that is going to be important for our work today is what it means to take a matrix and multiply it by basically this is that the second part here I'm going to call this a vector because it really is a vector. It's just unlike the vectors we saw in previous last semester. It's a vertical vector instead of a horizontal vector, but it's the same idea. If I want to multiply a matrix times a vector, um, the result is going to be a new vector. So it's still going to be made up of two pieces, a top and a bottom. And to figure out what goes into those two parts, it's basically about the dot product. Take my first row and dot it with a vector. So -4 times x plus 2 times y, right? Dot product means multiply and then add the results. And while it may look like those are two terms on top, or uh, two components on the top, really it's just one because we're adding them together. It's just that with x's and y's, we can't really combine them. And then if I did the bottom row dotted with that vector, it would be 3x plus 8y. So this is really what I mean by multiplying a matrix times a vector. It's just dot product. Take the first row times the dotted with the vector, take the second row dotted with a vector. If there's a third row, do that also, etc., etc. So this is what I mean by multiplying a matrix by a vector. Another thing we need to talk about is what's called the identity matrix. So the matrix I is called the identity matrix. Um, it's basically kind of like the number one, but for matrices. So first of all, the identity matrix is the matrix where the main diagonal is all ones. And remember, main diagonal means the entries where the row number is the same as the column number. So we have row 1, column 1, row 2, column 2, row 3, column 3. All those are ones. Oops. Come on. And all the other entries are zeros. So this is what we mean by the identity matrix. And the reason this identity is called the identity matrix, like I said, it's kind of like the number one, but it's a matrix, right? Because what is the number one, right? If you take any number times one, the result is just that number. Well, likewise, if I take any matrix times one, or times I, excuse me, the result is just that matrix again, A. So that's it. That's what we mean by the identity matrix. It's again, it's what you would multiply by without so that you don't actually change anything. Okay. Next up, this matrix, this vector is basically made up of a bunch of each entry is a function of x. This is we've actually worked with this already. This is exactly the same as when we had vector functions. Back last semester, when we had vector functions, it was basically a bunch of components. Each component was a function of t, and we could talk about the derivative, and we can talk about the integral, and so on. So I just want us to realize that if x of t here is a matrix, we could find x prime of t just by taking the derivative of each component. So it'd be 2 cosine 2t, 3e to the 3t, and 8. There's all my derivatives. We can also talk about the integral as just integrating each component. So the integral of sine t or sine 2t would be negative 1/2 cosine 2t plus a constant, of course. 1/3 e to the 3t plus another constant, right? They might be different constants, so we need different letters. And 4t squared minus t plus a third constant. So again, if we have a matrix made up of functions of t, we can, just like we always have been, we can still take the derivative, take the integral, exactly like we would expect. Okay, now let's get into really the most important part, the part that's going to affect the rest of our work in this chapter, eigenvalues and eigenvectors. So let's assume that A is an n by n matrix, meaning, and we haven't really talked about what do I mean by the size of a matrix, but basically what I mean is the first number is how many rows there are, the second number is how many columns there are, and so if it's n by n, that means it's a what we call a square matrix, because it has the same number of rows as it does columns. So the only way to talk about eigenvalues and eigenvectors are for square matrices. So a number lambda, by the way, that is the Greek letter lambda. I would write it like this. It's the same Greek letter as used for like half-life and physics and so on. Number lambda is an eigenvalue of A if there is some non-zero vector k such that A times k is equal to lambda times k. In other words, if I take a matrix and multiply it by this vector k, the result is no different than just some constant multiple of k. And whatever that multiple is, that's what we call the eigenvalue. And k is called an eigenvector. For anybody who's curious, that prefix eigen is, I think, is German. It basically just means characteristic. So this is the characteristic value, the characteristic vector of this matrix A. So first of all, just to see a real example of this, let's show that this vector k is an eigenvector of this matrix A. And again, to do that, what we want to show here is that when we do A times k, the result is just some constant multiple of k. So A is the matrix 0, -1, -3, 2, 3, 3, -2, 1, 1, times k, which was, let's see, 1, -1, 1. Okay, now we haven't done a lot of multiplying here. So let me just again say multiplying is basically the dot product. It's going to be the top row dotted with my column. So that would be 0 plus 1 minus 3. And then the second row dotted with the column would be 2 minus 3 plus 3. And then the third row dotted with my column would be -2 minus 1 plus 1. So the result here is -2, +2, -2, which is fine. I mean, that's the result of that product. Now we want to notice that this is the same as -2 times the vector 1, -1, 1, And of course, that is just the vector k. So what we found is that a times k is equal to negative 2 times k. That tells me two things. First of all, that tells me that k is an eigenvector, which is what we wanted. And it also tells me that its eigenvalue is negative 2. Eigenvectors and eigenvalues are associated with each other. So this vector corresponds to the eigenvalue negative 2. Now, the question becomes, how do we find these things? How do we find eigenvalues? How do we find eigenvectors? So to answer that question, let's look at this equation, okay, this relationship that really defines eigenvectors and eigenvalues. Now I'm going to take this equation and I'm going to move everything to the left side. I'm going to subtract lambda k from both sides. And so we get ak minus lambda k equals, now we want to be a little careful. Remember, this is a vector. And of course, a constant times a vector is just another vector. A vector minus a vector is a vector. Technically, this is the zero vector. Okay, so that's something important we should keep in mind because we are going to be using this. So keep in mind that it's actually the zero vector. It's not the number 0. Now, the next thing we want to do here is we want to notice that both terms have a k. And so we're going to factor out that k. So there's something that we really didn't get into it because we didn't get too into matrices. But the order that you multiply matrices does matter. And in fact, if you switch the order of multiplication of matrices, you might get a different answer, or you might even get a problem that's impossible. So notice that in both of these terms, the k is multiplied on the right. So when I factor this out, I'm going to have to factor out the k on the right side. And so I'm left with, well, I'm left with a minus lambda, but that doesn't really make any sense. Because it makes sense to have a matrix minus another matrix. In fact, we saw earlier when we did a plus b, we know how to add two matrices. It doesn't make sense to have a matrix minus a number. So what we're going to do to make this make sense is instead of a minus lambda, we're going to have an a minus lambda I. So this is how we're going to write it out. And so I'll write it right there. Now, I also want to think about, what does that lambda I mean? Well, so lambda I, we know that I is that matrix where the one's in the main diagonal, zeros everywhere else. We got that. So if I multiply this matrix by lambda, that means that each entry is multiplied by lambda. So the main diagonals all become lambdas, and then everything else becomes a bunch of zeros. So think about, because we're going to be using this a minus lambda I. Notice if I took any matrix A and I subtracted this lambda I matrix, notice that in the matrix A, the main diagonal will have lambda subtracted from each of those main diagonal entries. And all the entries will have 0 subtracted, meaning they won't change any. Something to keep in mind. We're going to work through this, so you'll see some examples for sure. Anyway, so we have a minus lambda I times k equals 0. Now, here's the thing. Again, I'm not getting too I'm not getting too deep into this, but that will be true only if the determinant of a minus lambda I is equal to 0. Again, I'm not going to get into why that's the case, but this is only true if the determinant of a minus lambda I is equal to 0. Let's remember determinants. We've used them plenty. Again, when we did the cross product, we were using a determinant to come up with that cross product. So just something to keep in mind, and so we'll certainly be doing determinants. So this is only true if the determinant of a minus lambda is equal to 0. That equation is what we're calling the characteristic equation of A, and that's what we're going to use to figure out what my lambdas are, what my eigenvalues are. So that's then the equation we're going to use to find lambdas. Okay, enough theory. Let's look at an example. Let's do a matrix here. So let's find the eigenvalues and eigenvectors of this matrix. A equals, so it's 1, 2, 1, 0, or 6, negative 1, 0. -1, -2, -1. Okay, so first off, we have to find the eigenvalues, which means we're going to take the determinant of a minus lambda I. So as we said, a minus lambda I is going to have lambdas subtracted from each of those main diagonal entries, and all the entries are going to stay exactly the same. And so now we're left finding the determinant of this 3 by 3 matrix. Well, let's work along the top row. So we'll have 1 minus lambda times its smaller matrix, minus 2, don't forget that alternating sign, so minus 2 times its smaller matrix, plus 1 times its smaller matrix. Okay. Okay, let's evaluate those smaller determinants. So we get 1 minus lambda times. So it looks like I'm going to get -1 minus lambda squared minus 0. That's interesting. Minus 2 times 6 times -1 minus lambda minus 0. Plus, let's see, -12 minus -1 times -1 minus lambda. Yeah. Okay, let's clean this up. So 1 minus lambda times, so FOIL that out, I'm going to get lambda squared plus 2 lambda plus 1. Let's see, looks like it'll be plus 12 lambda minus 12 minus 1 minus lambda. Okay, cleaning this up even more, we get negative lambda cubed minus lambda squared plus lambda plus 1 plus 11 lambda minus 1. And if I combine all the terms, we get negative lambda cubed minus lambda squared plus 12 lambda, and the 1's cancel. So if we have a 3 by 3 matrix, notice that my characteristic equation is going to be a cubic equation. Cubic equations are not always easy to solve, and so we're going to do a couple of examples today. Fortunately, in this example, the lambda the constant term canceled, which means that I can factor out a lambda. And in fact, I'm going to factor out a negative lambda just because I like my lead coefficient to be positive. So we get lambda squared plus lambda minus 12. Okay, again, in this case, it turned out that it wasn't that big a deal to factor it, but we want to just be aware that sometimes those cubic equations are going to be a little difficult. If I continue factoring, I'm going to get lambda plus 4 times lambda minus 3. And so I get 3 eigenvalues. My first one is going to be 3. My second one is -4. And my third one is 0. And by the way, the order in which you list these, it doesn't matter. I'm listing them in this order because it's going to be convenient to me to consider them each in this order, because we're not done yet. We found the eigenvalues, that's great, but we still have to find the eigenvectors. So now let's do that. And so let's start off with my lambda 1 equals 3. And let me just list them all out here. Lambda 2 is equal to -4. And lambda 3 is equal to 0. Okay. There's my space. Okay. What I've left here now to do is to find the eigenvectors. Well, I'm going to go back and look at that equation that we had before, a minus lambda I, but in this case, it's a minus 3i, right? In this example, or in this case, lambda is 3. So a minus lambda I times k is equal to 0. Let's figure out what a minus 3i is equal to. Now remember, a minus 3i means Subtract 3 from each part of the main diagonal, and don't do anything to the rest of it. So the result is going to give me -2, 2, 1, 6, -4, 0, -1, -2, -5. Sorry, that last one was -4. There we go. Okay. So I took the main diagonal entries of A and subtracted 3 from each of them, and I didn't change any of the other entries. Now times K. All right. Well, my goal here is to find K. So I don't know what the entries are for K, so I'll just call them A, B, and C equals. And again, the right side, it's not really 0. It's actually the 0 vector. Okay. So this is what my equation turns into. Now, let's write out the result of this product. So again, take the top row and dot it with the column. Gives me -2a plus 2b plus c. So the top row dotted with the column gives me that. That'll give me the top of my result. But notice that that's equal to the top of the matrix on the right side, which is 0. The second row dotted with my vector, so 6a minus 4b plus 0c is equal to the second component on the right side, which is 0. And then -a minus 2b minus 4c is also equal to 0. Okay, it appears now that what we have is a system of equations that we can solve. But here's the thing. You know how when you solve a system of equations, you're either going to get one solution or many solutions or no solutions, right? That's one of those three things is going to happen. Here's the thing. When it comes to solving for eigenvectors, you're always going to get many solutions. In other words, eigenvectors are not unique. There's lots of correct eigenvectors. We just need to find one of them. So let me say one more time. Eigenvectors are not unique. What that means is that when I'm solving this equation, or solving the system, I expect to get one independent variable, meaning I expect to be able to pick a number for one of these variables, A, B, or C. But what that also means is I'm allowed to ignore one of these equations. Now, in other examples later on, it will be obvious which equations to ignore because one equation will clearly be a multiple of the other. Here, it's not clear. Here, there are not two equations that clearly say the same thing. So as I said, I'm allowed to ignore one of the equations. Ignore whichever one you want. It doesn't matter. I'm going to ignore the last one just because I got to pick one and I'm going to pick that one. And so I'm going to just solve the system with those first two equations. So I'm going to notice that this bottom equation tells me that A is equal to 2/3 B. Now, when I get my eigenvector, and I'll call this K1 because it's my first eigenvector, I'm going to put numbers for A, B, and C, of course. And as I said, as I'm working through these problems, I expect one of my variables to be independent, where I get to pick whatever it is, whatever I want. So in this case, I'm going to pick a number for B. Now, so I can pick any number I want for B. Well, any number but 0. Don't pick 0 for B, because if B is 0, then A is 0, C will be 0. Remember, eigenvectors have to be non-zero vectors. But again, pick any number you want for B. You can pick 1, you can pick 12, you can pick whatever number you want. I'm going to pick 3, simply because if I plug in 3 for B, I end up getting 2 for A. And it just works out nicely, and if I can avoid fractions, I'm going to. But again, any number but 0 would be a perfectly great choice. Now that I know A and B, I can plug them into the first equation. So we get -2 times 2 plus 2 times 3 plus C is equal to 0. And if I solve that, I'm going to get C equals -2. So I've got the third part of my eigenvector. Now, I didn't use that last equation. If you want to, and I certainly don't require you to, But if you want to, you can take this answer and plug it in and verify that the bottom equation also is satisfied. So negative a minus 2 times b minus 4 times c equals 0. Well, negative 2 minus 6 plus 8 is 0. Yeah, it works, okay? Again, I don't expect you to ever do that, but if you're ever concerned about ignoring one of the equations, you can go back and show that, yeah, your answer does also satisfy that equation. Okay, let's move on to lambda 2 equals negative 4. So again, I'm going to do a minus negative 4 times I times k is equal to 0. So this time I'm going to take the main diagonal and add 4 to each of those entries. So if I add 4, I get 5, 2, 1, 6, 3, 0, negative 1, negative 2, 3. Times k, which is a, b, c, equals 0, 0, 0. Once again, I know that I'm allowed to ignore one of the equations, and in this case, again, there is not two equations that are clearly multiples of each other, so I can pick any equation I want to ignore. In this case, I'm going to ignore the top equation. I have no reason to. That's the way I chose to go. So the second equation tells me 6a plus 3b equals 0. The bottom equation says negative a minus 2b plus 3c is equal to 0. This equation I can solve for b. I get b is equal to negative 2a. And so in my vector, this time I'm going to pick whatever I want for a. Because if I pick a equals, say, 1, b is negative 2. And then if I plug those both into the last equation, we get negative 1 minus 2 times negative 2 plus 3c is equal to 0. It looks like I'm getting c equals negative 1, I believe. Again, if I'm not sure, I can go back to the top equation that I ignored. 5 times a plus 2 times b plus 1 times c is equal to 0. It works out. So if you're ever unsure if you're correct, again, the one that we ignored will help us. So we have our second eigenvector here, 1, negative 2, negative 1. Let's do the third eigenvector, or eigenvalue. So a minus 0i this time times k is equal to 0. Okay, I'm going to subtract nothing, so I'm just going to use a as is. We have 1, 2, 1, 6, negative 1, 0, negative 1, negative 2, negative 1 times ABC equals 0. Okay, so I mentioned that sometimes it's going to be obvious which equation you should ignore. Please notice in this example, the top equation is just a multiple of the bottom equation, right? Take the top one times negative 1, you'll get the bottom. If two equations are obviously multiples of each other, make sure that you ignore one of those two. So I'm going to do the top equation and the second equation. So 6a minus b equals 0. Yeah, so just make sure you ignore that bottom one because it's clearly a multiple of the top one. This tells me that b is equal to 6a. So for my third vector, if a is 1, then b will be 6. And then plug that in to find c. So we get 1 plus 2 times 6 plus c equals 0. We get c is equal to negative 13. And I've got my third eigenvector. All right, there we go. We're going to do a couple more examples, but this is basically the idea of how to find eigenvalues and eigenvectors. And as I said, this is the stuff that is really going to come up again in the rest of this chapter. So it's definitely worth your time to learn how to do it. On the homework, you're going to make sure you do a bunch of these so you can practice finding eigenvalues and eigenvectors. But of course, as I said, we're going to continue using this throughout this chapter. So it will definitely come up, and we'll continue practicing it together. Okay, let's find the eigenvalues and eigenvectors for this matrix. So let's see here. So again, we start off by finding the determinant of a minus lambda I. So I'm going to subtract lambda from the main diagonal. Find the determinant. So we get 3 minus lambda times 7 minus lambda minus negative 4. So I get lambda squared minus 10 lambda plus 21 plus another 4 gives me plus 25. Factor. And so in this case, I only got one eigenvalue, which is 5. It's fine. It's okay. We just got one eigenvalue. Nothing wrong with that. Let's find the eigenvector that goes along with it. So if lambda is equal to 5, we're going to do a minus 5I times k is equal to 0. So if I subtract 5 from the main diagonal, I get negative 2, 4, negative 1, 2 times k, which here there's only two entries, a and b. Once again, I'm going to observe that the top row is a multiple of the bottom row, so it's clear that one of them can be ignored. And so we get negative a plus 2b is equal to 0. So a is equal to 2b. So if, in this case, if I pick, like, say, 1 for b, I can pick whatever I want for b, except for 0. And so a is going to be 2 times that, so 2. Okay. In the last example, it was a 3 by 3 matrix. We got 3 eigenvalues, 3 eigenvectors. Here is a 2 by 2 matrix. We might get 2 eigenvalues and 2 eigenvectors, but in this case, we end up getting only one of them, one eigenvalue and one eigenvector. All right, let's take a look at one more example here. Let's find the eigenvalues and eigenvectors of this matrix. Once again, we're going to start off with the determinant of a minus lambda I. So I'm going to subtract lambda from the main diagonal. So we have 9 minus lambda times its smaller matrix minus 1 times its smaller matrix plus 1 times its smaller matrix. So this becomes 9 minus lambda times 9 minus lambda squared minus 1 minus, let's see, this will be 9 minus lambda minus 1 plus 1 minus 9 minus lambda. Okay, so we get 9 minus lambda times, let's see, if I FOIL that out, it'll be lambda squared minus 18 lambda plus 81, but then minus 1 gives me just plus 80. And then the rest of this I'm going to have, let's see, it'll be lambda minus 8 plus lambda minus 8. Cool. Okay, now let me stop here for a second, because as I mentioned earlier, if you are starting with a 3 by 3 matrix, notice your characteristic equation will be cubic, and solving cubic equations can be a pain. So my advice would be go slowly with simplifying, because if you can find a nice algebra trick, it might save you the effort of factoring the cubic. So let me point out here in this example, if I factor that quadratic there, it becomes lambda minus 8 times lambda minus 10. And then over here, I'm getting 2 times lambda minus 8. The observation is I have two terms. Both terms have a lambda minus 8. So if you go slowly, and if you notice that, and listen, it's not always going to work, but if it does, it can save you a lot of grief factoring that cubic. I can factor out that lambda minus 8, and now I'm left with 9 minus lambda times 10 times lambda minus 10 plus 2 In other words, what I'm left with now is a quadratic, and that certainly makes life a lot nicer. So if I FOIL that out, I'm going to get negative lambda squared plus 10 plus 9, so plus 19 lambda minus 90, but then plus 2 more gives me minus 88. Let me pull out a negative. So this becomes lambda squared minus 19 lambda plus 88. And if I factor that some more, that factors as lambda minus 11 times lambda minus 8. And so I'll just make that a squared there. So finally, if I set this equal to 0, I get lambda 1 equals 11, and lambda 2 is equal to 8. Okay, so we got, in this case, we ended up with 2 eigenvalues, one of which repeated twice. Great. Now let's look at the eigenvectors. So for lambda 1 equals 11, so we're going to do here a minus 11I times k equals 0. So I'm going to subtract 11 from the main diagonal times k equals 0. Okay. In this case, none of the rows are obviously multiples of the others, so I can pick whichever row I want, whichever 2 rows I want. So let's do negative 2a plus b plus c equals 0, and a minus 2b plus c equals 0. Okay. Remember, we're solving a system of equations. So in this case, if I just subtract the rows, or subtract the equations, I can make the c go away. So I get negative 3a plus 3b equals 0. So I get a is equal to b. So in my eigenvector, I'll just let a and b both be, again, any number you want other than 0 is great. I'll just pick ones. And then if I go back to the top equation, whoops, negative 2 times 1 plus 1 plus c is equal to 0, I end up finding out that c is also going to be 1. So my first eigenvector is the vector 1, 1, 1. Okay. Right, let's see here. So now for lambda 2 equals 8, again, we're going to do a minus 8I times k is equal to 0. So if I subtract 8 from the main diagonal, I get 1, 1, 1, 1, 1, 1, 1, 1, 1, fairly boring, times k is equal to 0, 0, 0. Okay, we need to make an observation here. And the observation here is that all 3 rows are the same thing. Or even if they weren't all the same thing, if they were all multiples of each other, that would be just as bad. All 3 rows tell me the same thing, which means I only need one of them. So that would be a plus b plus c is equal to 0. And if I solve for c, c is equal to negative a minus b. In other words, because all 3 rows said the same thing, I can ignore 2 of them this time. And as a result, I ended up with 2 independent variables. In this case, it's a and b. And because I got 2 independent variables, I'm actually going to get 2 different eigenvectors from this. Now, because a and b are both independent, I get to pick any number I want for a, I get to pick any number I want for b. And again, any combination is fine. You can pick any number you want for a and b. So like, let's say you pick 1 and 0. C is going to be negative a plus or minus b, which is negative 1. And now for K3, I'm going to pick any other combination. How about 0 and 1? And as the result would be the C is negative 1. Okay, these are 2 good eigenvectors. Now, I don't need any more. I found 2 answers. I just want to point out there are lots of other correct ones that I could pick. What if I picked that A and B were like, I don't know, 2 and 5? Well, then C would be -7 from this equation. Let's say I picked, I don't know, -6 and 1. Well, then C would be 5, I think. Yeah, so you'd be 5. So again, these are not part of my answer. I just want you guys to realize that there are lots of correct answers out there. Okay, this is just 2 out of many. But again, to kind of get back to the confusing part here, I had an eigenvalue that repeated twice. 8 repeated twice. And in this case, it repeated twice, and I was able to get 2 eigenvectors from that repeating eigenvalue. Now, that doesn't always happen, right? We had this example right here. The eigenvalue repeated twice. I only had 1 eigenvalue. I only got 1 eigenvector from it, and that's fine. Sometimes an eigenvalue repeats twice, but you only get a single eigenvector from it, and that's okay. But sometimes an eigenvalue repeats twice, and you get 2 vectors from that one value. So now again, the question is, how do you know when that happens? The answer is this. If all 3 equations tell you the same thing, that's what's happening here. If all 3 equations tell you the same thing, that means that you are able to ignore 2 equations. Notice over here we ignored 1 equation, we got 1 vector as a result. If you're able to ignore 2 equations, then you're going to end up with 2 independent variables where you get to pick whatever numbers you want. And however many independent variables you have, that's the same number of vectors you're going to get as a result. So if you can ignore 2 equations, then you get 2 independent variables and you get 2 eigenvectors. It's kind of confusing, I know. And in later lessons, we're going to return to this idea and just kind of refresh your memory, if nothing else, about identifying how many. So just keep in mind, if you have a 3 by 3 matrix, you are going to get at most 3 eigenvalues, although there could be less. You're going to get at most 3 eigenvectors, although there could be less. Right? Again, here's an example. It's a 2 by 2 matrix. We could have gotten 2 eigenvectors, but in this case, we only got 1. Here's a 3 by 3 matrix. We could have gotten 3 eigenvectors. And in this case, it turns out we did get 3 eigenvectors because my repeating eigenvalue resulted in 2 eigenvectors. Okay, it's confusing, I know. And unfortunately, it is on that confusing note that we're going to finish. So that is the end of the lesson. Thank you very much for watching.